So, we're going to be talking about today, we're going to talk more conditional today. And just begin by remembering what the conditional statement is. The conditional statement,
P implies Q. So, words, if P statement live in Wenatchee and Q is the statement I live in Washington, to say P implies Q means that if I live in Wenatchee, then I live in Washington. We can make a table for this. We have true, true, false, false, true, true, false. And we said that the condition only false if the antecedent happened and the consequent didn't. This time false shows up. And we use that example. If I get elected mayor, then everybody get a puppy. I got elected, you got a puppy, I'm not. I got elected, you didn't get a puppy, I did not get elected, but you anyway, I'm still not a liar. I did not get elected, you did, I still didn't lie. So our conditional statement is Q. Let's talk about Converse shoes for a second. Something that I always thought was a little goofy about their logo is on the inside of the shoe. If you look at a pair of Adidas or a pair of Nike, the logo will be on the inside and outside, or just the outside. But with Converse, it's the wrong side. It's backwards in my brain. And I have that odd. So just like a shoe where it's backwards, the converse of conditional statement is the conditional statement but backwards. Instead of implies Q, we have Q implies P. So with this, if I live in Wenatchee, then I live in Washington. If I turned that around, we would say if I live in Washington, then I live in Wenatchee. Is that always, if I live in Washington, then I live in Wenatchee? No, that's not always going to be the case. We can do a truth table for this. Q implies P. Now we're looking at it going backwards. Q implies P will only be false if Q is true and P is false. And if you want to list these out, that's fine. Q is true, false, true, false. The antecedent has to be true, and the consequent has to be false for us to get a false out of a conditional statement. Otherwise, it's true. And so the truth value of the converse would live right there. The inverse and the contrapositive are very similar to the conditional and the converse, except for the inverse we would say not P implies not Q. And if I was going to use this I live in Wenatchee, I live in Washington example, it would say if I don't live in Wenatchee, then I don't live in Washington.
So let's make a truth table for this. I'm going to clear out, there's a couple red dots on the screen. I'm going to make a truth table for this, so I have true, true, false, false, true, false, true, false. And we're doing not P implies not Q. So I'm going to write down the negations for P and the negations for Q. That's going to be false, false, true, true. And then false, true, false, true. Remember, the antecedent has to be true, and the consequent has to be false for us to get a false out of a conditional statement. Otherwise, it's all true. And so the truth values for this would be right there. I'm just going to box these because I'm boxing all of them. It just feels consistent. The contrapositive, very similar to the converse, except we're going to say not Q implies not P. So, with this example, we're going to say not Q, that's if I don't live in Washington, then I don't live in Wenatchee. Truth table for that. And we're going to say not Q implies not P. I have not Q is false, true, false, true. Not P is false, false, true, true. For a conditional statement, again, the only time false shows up is if my antecedent is true and my consequent is false. Otherwise, everything else is true. Okay. If you have not done so already, go ahead and practice these truth tables below. And for our purposes, go ahead and flip your paper over. We're going to talk about some common translations for if P then Q. Or you'll hear me more commonly say P implies Q. So, a little too high. There we go. One way that we can say this, we can say if P then Q. Pretty common. If then. We can say if P, comma Q, or P implies Q, or P only if Q. P is sufficient for Q. Q is necessary for P. We can say all P are Q, or Q if P. Those are the variations for P implies Q. I'm going to work through one of these examples. Here, if it ain't broke, don't fix it. So this is that if P, comma, Q. If it ain't broke, don't fix it. It ain't broke, that's going to be P. Don't fix it is going to be Q. Here I have P implies Q. The converse is backwards. The converse of this is going to be Q implies P. So in other words, Q implies P, we can say if you didn't fix it, then it wasn't broken. And we're adjusting for grammar to make the sentence sound more proper. If you didn't fix it, then it wasn't broken. The inverse is, and I'm actually going to write this over to the side here. You don't have to erase it. I'm just going to rewrite it here. Q implies P. The inverse is not P implies not Q. So not P, that would be, instead of it ain't broke, we're going to say it is broke. I'm going to say it is broken because I just can't help myself. If it's broken, to negate don't fix it would be do fix it. So if it is broken, then fix it would be not P implies not Q. The contrapositive is not Q implies not P. Not Q is the negation of don't fix it, which is do fix it. So we say, whoops. If you did fix it, then to negate P says it isn't broken. To negate that, we would say it is broken. I'm adjusting for grammar. If you did fix it, then it was broken. I'm going to have you do 2, 3, and 4, please. And then let's talk about the biconditional. Biconditional statements we read this as P if and only if Q. Mathematicians tend to not write so much, so we abbreviate if and only if as P, IFF, Q. IFF means if and only if. To write that in symbols, we would say P implies Q and Q implies P. The arrow goes both ways. And so if we have P, if and only if Q, notice that the arrow goes in both directions. P implies Q and Q implies P. If I think of it like this, I can say that P if and only if Q. I don't like the way I wrote that. Let me fix that. Okay. I can say P, if and only if Q, is equivalent to P implies Q and Q implies P. So these are equivalent statements, and the implication has to go both ways. Let's look at the truth table for this. Remember, we only get our false when the antecedent is true and the consequent is false. So if the antecedent is true and the consequent is false, going in this direction, I get a false. If the antecedent is true, now we're going to look in the other direction. Antecedent is true, the consequent is false. I get a false there. Otherwise, it's going to be true and true. And there would be the truth value for this table. Let's do a couple examples together. 6 equals 5. That's false. 12 does not equal 12. That's false. If I have false, if and only if false, I need to look at it in both directions. If I go in this direction, it works. Whoa, there we go. Going from false implies false works. Going false implies false in the other direction works. This would actually be true. 5 plus 2 equals 10. That's false. We have false if and only if 17 plus 19 is 36. That's true. False if and only if true. Going in this direction, the antecedent is false, the consequent is true. That works. Going in the other direction, the antecedent is true, the consequent is false. That does not work. So we would say that this is false. 7 is an element of, remember what this R is? That is the real numbers. This Q is the rational numbers. Q is for quotient. So we're saying -7 is an element of the reals. That's true. -7 is an element of the rationals. That's also true. If I have true, if and only if true, it works going from left to right. It works going from right to left. This would be true. Okay, I think that's going to wrap up this section 3-4. So thank you so much. Have a wonderful day.